Hi, in this video, I want to show you the application of the Bayes rule for screening tests. First, let us give some definitions. Define a screening test outcome as T and the true disease status D. Both T and D are binary variables. Then T plus is screening positive, T minus is screening negative, D plus is disease positive, D minus is disease negative. Then we can define the conditional probability of given D positive, the probability of T positive. This is called the sensitivity of the screening test. Probability of T minus given D minus. So this is called the specificity of the screening test. So the sensitivity is the conditional probability of given is a true disease status. What's the probability you will get a positive screening test? And the specificity of the screening test is the conditional probability given it's a disease negative. What is the probability you will get a test negative? Okay. Both sensitivity and specificity are performance indices of the screening test itself. Okay. And we can define probability of D plus given T plus. This is called the predictive value positive of the screening test. And sometimes we use PV plus as the notation. And probability of T minus given T minus is the predictive value negative of the screening test. And sometimes we use PV minus as the notation. Now the predictive value positive and predictive value negative, they are showing the ability when you use the screening test to actually predict the true disease status. Okay, so this is when you're actually using the screening test to screening new cases. Okay, and we can also look at probability of D minus given T plus. So given is a disease positive, no, given the test negative, sorry, given the test positive, what is the probability of you get it? It's actually not a disease case. This is called the false positive rate, and it is 1 minus the predictive value of positive. Okay. And similarly, the probability of D plus given T minus. So the probability given that is test negative, what the probability is actually a disease positive. So this is called the false negative rate. And it's the 1 minus the predictive value of negative. And probability of D plus, that's the disease prevalence. Okay. All right. And if you apply the Bayes rule, you can easily derive the following formulas. PV plus equal to sensitivity times probability of D positive divided by sensitivity times probability of D positive plus 1 minus specificity times 1 minus probability of D plus. Okay, so you can see the predictive value positive can be computed using sensitivity, specificity, and disease prevalence. Similarly, PV negative equals specificity times 1 minus probability of D plus divided by sensitivity times 1 minus probability of D positive plus 1 minus sensitivity times probability D positive. Okay. So you can see the PV plus the PV minus, they are actually influenced by the disease prevalence. So the disease prevalence can have an impact on the PV plus and PV minus. So here is an example on HIV screening. So the primary screening tests used for HIV in the United States is the HIV-1/2 antigen antibody immunoassay. This test detects both HIV-1 and HIV-2 antibodies, as well as the HIV-1P24 antigen in blood. It is recommended for routine laboratory-based HIV screening test and is approved by the U.S. Food and Drug Administration, FDA. It has a sensitivity of 99.85% and a specificity of 99.9%. So the numbers looks really good, very high sensitivity, very high specificity. So is it really good for doing screening? Let's take a look. The current prevalence of HIV in the United States is estimated at approximately 1.2 million people living with HIV. This includes both diagnosed and undiagnosed individuals. About 13% of those infected are unaware of their status. The prevalence rate is about 11.3 per 100,000 people as of the most recent data available from 2022 to 2025. So this translates to a prevalence of 0.0113%. Okay. Now let's write down the data here. Sensitivity is about 99.85%, or 0.9985. Specificity is about 99.9%, or 0.999. And prevalence is about 0.0113%, or 0.000113. So if we use that formula for PV plus, and we plug in the numbers, the final results is about 0.1014. So the conclusion is when the test is positive, there's about a 10.14% chance that the person actually have HIV. So this is really bad, right? So you really cannot use this test to predict the actual HIV positive. It's got like 10% chance, okay? This is really showing us the impact of very low prevalence on the predictive value despite high sensitivity and specificity. So even you have a very good screening test with a very high sensitivity and specificity, they may still fail when you actually try to use it to diagnose or test cases in the population, right? And here's an exercise you can do if you want. Compute the predictive value negative of the screening test if used in the US population. And I will not give the details, but you're going to get a very, very, very high predictive value of negative, like 99.999%. So what's the take-home message here? So this test is very good at ruling out cases, okay? But it's not really good at detecting new cases. That's kind of the implication of our calculation here. So if you want to really also want to use it to detect the HIV positive in US population, probably want to pair it with another test which has a high PV plus. Okay. All right. I hope this example shows you the useful application of Bayes rule in screening tests. Thanks for watching.